Alright, welcome to another draft physics video presentation. Unfortunately, I have had a little trouble with these recordings, so I did a video yesterday and it didn't process correctly, completely. What the hell happened there? It's always something. Let me pause for a moment and fix that. Always something, sort of, mostly. Should be working. Anyway, alright, so this video will be a complement to the experiments video, and so I will link those two videos together in some way or other in descriptions or something, so people concentrate on them as the important videos in terms of responding in some sort of coherent way to why I have these objections about conventional physics and its credibility. And frankly, if you want to make a counter argument, it has to be relevant to the points raised. Yeah, so this will be the question one, like all the unanswered questions. I'll try to go through them on this list and give you a brief illustration of them, those that can be illustrated and such. And I did deal with some comments in the last video, and unfortunately they've been deleted now. So I'll try to reconstruct what I can of those arguments and such. Okay, so we'll move on. So the first group of experiments are the ones fundamental to the whole idea of quantum mechanics. It's all, as Feynman would put it, it's the two-slit experiment is the experiment in physics, defining this whole argument. But the real key is you just start with the single slit, and the fact is they say it's proof, nail in the coffin evidence of wave-like behavior, all of these verbiage they use. So the first thing I point out is that the pattern is the simplest pattern you can get, on and off. There's no simpler pattern in the universe than on and off. So it's not a very complex pattern, and one shouldn't say something like, well, we as physicists know what that means, because you really don't. So anyway, single slit in water does something quite simple. It does this. Okay? Nothing surprising. No interference, no pattern, nothing. In light, something quite different happens. They like to always illustrate it as being, oh, it's just this little tiny bit of pattern. They do it like this because they make the slit really small. But if you make the slit fairly wide, you get a nice, whole bunch of little bits of interference. You get the full dotted line treatment. You can't see that very well, but you'll have to just trust me on that one. Anyway, so the idea is that two waves are created, and that these two waves interfere with each other, and there's no explanation for why two waves. One wave goes in, two waves come out. No explanation for why. The one kind of a semi-explanation goes all the way back, 250, 300 years to Huygens, and some idea that there's actually an infinite number of little waves. So when a photon goes in, there's really an infinite amount of photon going in, and it creates an infinite number of little waves, and the little tiny waves all add up to two waves somehow. And it still doesn't make any sense. There's no reason why it would turn into two waves. So they still have no rational reasoning for why there's two waves in the single slit. All right. So the question is, why do you think this is nail in the coffin evidence where it doesn't fit the reality? It's not demonstrating wave-like behavior. It's nothing like a wave in the single slit. Double slit. Now the actual pattern produced, they just do this stupid thing here. They say, oh, two openings, now I have two waves. So we're supposed to believe that because of Huygens, two waves are created here on each one of these single slits, right? So if their principle for the single slit is correct, how come it doesn't apply in the double slit? How come all of a sudden Huygens, it forgets to Huygens? It forgets that it's supposed to make two waves here from Huygens. Now it forgets that principle and says, forget it, that doesn't really happen. And now it's only one wave. And now they can make these two waves interact with each other and say, we've created a bar pattern, an on-off pattern. So we've created the pattern. Well, unfortunately, that's not the pattern. Okay, the pattern does that, and then it turns to nothing, and then it starts again and makes another pattern, right? Sorry about not much I can do about the glare, unfortunately. Not much I can do. I can try that. It's a little better. have to do. I have to be able to see the damn thing. So anyway, so there's a pattern going both ways this way, but you have these huge nothings here. So their mathematics, the formula they always throw at you, will not do this. It won't recognize the actual pattern. So the actual pattern has nothing to do with their math. It has nothing to do with these two waves. These two waves won't do this. They won't make this nothing here. They won't make this nothing here. So it doesn't fit the evidence. It's not, frankly, close enough to say something like it's nail in the coffin evidence that we have the right theory, when their math doesn't work, in spite of the fact that they say it's the most reliable and dependable and accurate math in the history of mankind. Well, the facts don't indicate that that's the truth. The facts indicate that no, it's insufficient, it's incomplete, it doesn't get the right answer. Something's wrong with their theory, yet they won't admit that simple fact. It doesn't come up with the right results. So those are two examples. Let's see, what else do we have? Oh yeah, so now I can bring up they do this experiment in other ways using radar with two sources, and they'll have the same assumptions about what's taking place, a bunch of this interference stuff, and then you're getting a pattern. And the truth is that the math for jamming, that is jamming, just the signals are jammed because we can't receive you can't receive two radio stations at the same time. If two radio stations are sending a signal and the two radio stations are out of phase, you won't get any signal at all. The receiver will just say, F you, I can't do that. Okay, you have to send me one signal or the other signal if they're the same frequency. I can't separate a bunch of different signals unless you make a directional antenna. The antenna can't tell. And so jamming would explain exactly why this source and this source create interferences, because as soon as they go out of phase, that as soon as this distance is out of phase with this distance, so to speak, as long as there's a half wavelength here, half wavelength too much distance, yeah, there'll be nothing here because you're sending two frequencies that are the same frequency, and you're sending the two frequencies out of phase. And so the receiver is going to say, I can't tell which one you want me to detect. I'm seeing basically the receiver seeing this. Okay, it's seeing double the frequency. It can't receive that frequency because you haven't tuned it to that frequency. So it's not going to see it there at all. So jamming completely explains the phenomenon. So the first obligation, the first question I'd say, why can't jamming be the answer? What disqualifies jamming? And I'd argue when you put an audio signal on it, jamming also works, because even though this is the real signal is twice as strong here as it should be. It's 2x and it's 2x. Well, the explanation is because when you're putting an audio signal on, you're taking a signal that's this and you're converting it into an audio signal, which is you're turning into a sine wave. So you're turning this little line into this volume of signal. So when you increase, when you amplify, you end up creating twice as much signal through the amplifying process. But anyway, that's sort of a more technical argument. But the point is jamming does answer it. And as I pointed out in the experiments videos, there are experiments they could do that prove that these two waves don't have to interact with each other at all. I can just have them come from two different directions, and then I can just move one of the sources to change the phase. That is, change where the antenna is based on where the signal is going to hit the phase of the signal. So, and as soon as they're out of phase, I'm not going to receive any signal. The fact is, I can just move one of the sources, and as I move the source, the signal will go on, off, on, off, on, off, on, off. And proving that these two waves don't have to involve each other at all. They don't have to influence each other at all for there to be jamming, not jamming, jamming, not jamming. All right, so another nail, okay, made available for hammering into the coffin that conventional physics has the wrong premise, the wrong idea. This isn't about waves. Waves are a group phenomenon. They're not what individual photons are doing, and there are better explanations. As I've pointed out, a better explanation of what a photon is. All right, lensing, gravitational lensing. So they always talk about Einstein. Einstein, they call it Einstein rings. So this idea that there's an object behind another object. So there's an object, there's another object behind it we can't see. And somehow that object makes this perfect little ring. Okay, well, Einstein said, okay, what did Einstein really say? Say, we'll never see one. Because, frankly, the only way you can see it, it has to be just a tiny area in space. So in one tiny place, the bending is just right to create a focus for here, you know, us here on Earth, let's say. And so we can see the ring from each location because it's exactly the same amount of bending. So the light comes out, it bends into this cone, and the cone could be seen by us from one position. Now, if a photon comes a little bit like in this area, well, it's going to get bent too much by gravity, so it won't get to us. And if the photon comes out here, it's going to get bent too little, and we're not going to see it. So those are the only two choices. Too much bending, too little bending. There's only one tiny little shred that would be the right amount of bending. So Einstein said, yes, you'll never see one. Because it's not enough, you can't cover enough space. Because of the inverse square law of gravity, you're not going to be able to have enough area to create any kind of enough of an effect. So why was Einstein wrong is the question. They claim they have pictures of Einstein rings. Einstein said you can't take a picture of it. So why was Einstein wrong would be the question. What new fact showed up to make it possible for something to happen that Einstein said wouldn't happen? Now this is also related to gravitational waves, which again Einstein said you'll never see because they're way too weak. There's not enough gravitational difference between two things being in this arrangement, two things being in this arrangement. This arrangement technically has less gravity because you're spreading the gravity this way. Okay, where this, the gravity is in one consistent direction. So from a point of view of this looks stronger than this. Alright, so it's a tiny bit of difference. So as something orbits, as two things orbit each other, swirling around, they would be in this position versus this position. And technically, this position would appear that the center of gravity is here, and in this position, the center of gravity would be back here. So there's a tiny little difference, and so there would be this little tiny tug in the gravity, little tiny change. Einstein said, way too small, never see it, never detect it, impossible. Yet now they made it possible. So why was Einstein wrong again? Einstein never, they keep saying it's something to do with Einstein. Einstein never had any theory that you could take two physical masses and somehow combine these two objects and then take a piece of this mass out, take a piece of this mass out, and convert those pieces of mass into bent space. And that's what they claim LIGO is doing. They claim two black holes crash into each other and part of the mass actually turns into something called bent space or gravity by some kind of magic. Einstein never said gravity was a force you could make out of matter. So again, why are they putting Einstein's name on something they invented? So I want to get back to lensing. All right. So okay, we know. So the Einstein ring, why? We also know that they traditionally draw this and claim that they're magnifying an image. That is, they're taking something that's way far away and they're making it bigger, okay, in the lens, and then we're seeing it, here on Earth. Well, frankly, the lens is exactly the wrong shape. A traditional magnifying lens bends the light more on the outside and less on the inside, obviously creating a focal point. Gravity does exactly the opposite. The lens bends less on the outside and more on the inside. So it's, essentially can't even really draw the lines totally appropriate to the circumstance. I don't even know how to draw the lens because it's the wrong shape. But anyway, well, I'll just do it like this so you get the idea. It's exactly the opposite of a magnifying lens. So it's the place where it needs to bend the light the most, there's the least gravity, so it bends it the least. The place it needs to bend it the least, that is where you want the light to go straight through, it's bending it the most. So obviously it's not going to work as a magnifying lens. So you're not going to make small objects far away close because it can't work. There's no theory for this at all, that the wrong shaped lens can magnify anything. So again, why is that incorrect? Why is this wrong shape, the opposite shaped lens, still a magnifying lens? How can it do exactly what a magnifying lens can do when logically it can't? Now, even if you think you can have an image, the other thing to understand is the thing they're seeing is probably the same size as almost the same size as the lens. Now, it's really hard to magnify something, okay, with a lens that's the same size as the thing you're trying to magnify. It's kind of difficult because you've got a bunch of parallel lines coming in, and the parallel lines are going to bend by gravity. That is, these are going to go straight, and the ones you need to bend very little are going to be going this way and that way. So you're going to have very likely, you're not going to collect a lot of light. You have no way of collecting a bunch of light to bring it to a focus. That's the other key to seeing objects that are very far away. Is the whole point is because they're so far away, you're getting very few photons. So the idea is a magnifying lens collects a whole bunch of rays and sends all of the rays to you. So you're getting a brighter image because you're condensing a bunch of rays into one point. You're taking them and putting them on one point. There's just no hope of the wrong shaped lens doing that. It's because it's going to scatter light in all kinds of directions that aren't going to be anywhere near you. So there's no way you could ever magnify the brightness of an image. So it's certainly not going to make anything brighter. There's no theory for it, is the point. It can't be done theoretically. I had the idea of this, the idea that whole objects are seen. So what they do is they have like galaxies, and distant galaxies will end up being, their argument is that you have some objects here that are creating gravity, and that somehow this object far away ends up creating an image of it here in the lens, and then we see that object here. Now, the only way that can happen is the light from all these distant points has to somehow, okay, be bent the right amount, which is frankly less here and more on the outside. So how does that happen? How does the lens, when it's bending the wrong amount, the place it needs a lot of bending, it's less bending. The place it needs no bending, there's more bending. How can you possibly make an image? The inverse square law isn't a very good lens shape. So again, this gravity is changing by the inverse square law. So the amount of bending is not changing by some nice proportional lens shape. It's the gravity lens. And so there's no likelihood that any object of any size would able to bend the photons to a focus and get them to one point here on Earth for us to view them. So there's just no chance of this working theoretically. Alright, the other thing is a distance problem. Nobody talks about this one either. Let's say that you did see an object in space and it was like on its side, like a galaxy. A galaxy could be seen in the pancake form, like the center with the swirling arms. But what if you're looking at it on its side? Well, the real problem is this galaxy can be 100,000 light years, okay, across. So the light coming from the back of the galaxy would be 100,000 years older than the light coming from the front. The photons would be that much older. So the light coming from this part of the galaxy would be 100,000 years difference than the light coming from this back portion. And that's a huge amount of time. So in 100,000 years, they're saying this galaxy didn't move. Because the only way you could actually see the image, right? The only way you could actually see the galaxy in its proper shape and form is you'd have to believe that the light coming from the much more distant part of the galaxy, that somehow that photon is the same. The photons haven't changed any. That is, the position of the galaxy didn't change in space. And somehow you're able to see these two photons at the same time. One that's 100,000 years older than the other one. And you're going to see them now at the same time. So one of them's a really old, 100,000-year-old photon, and one's a today kind of photon. It left this point at the same time. It reached this point. And one of them was already 100,000 years into its travel. And then they both came down. There's no chance that this galaxy didn't move in 100,000 years. So, what sense does some of this stuff make? So obviously when we see an image of a galaxy on its side, we see it as this kind of fuzzy thing with this stuff here in the middle and the top. Well, all this stuff could all be from the movement of the galaxy. The fact is the galaxy is moving, and the light you're seeing from parts of it are much older than the light you're seeing from other parts of it. So the one part is, is where it is at that point, but the other part light you see was 100,000 years older, so it's in the wrong position because the galaxy did in fact move. You have to understand all these galactic images are all worked. You see one of these images of a nebula or something else, they've taken data from all kinds of different sources, all kinds of different infrared images, X-ray images, radio images, and they combine all these image data to make a new image. And so the image isn't really a photograph. So anyway, so some of it can be quite deceptive. But I'm just saying it's a physical problem that they don't have any explanation for. All right, object be seen. All right, why no repeat of the Eddington experiment? So again, you have this simple experiment. The sun's here. There's a star in the background. It's going to go, the light's going to have to travel through the sun's gravity to get to us, and it's going to be bent because of that process by their theory. And again, this is the 2x thing, right? Einstein just invented this idea that the only thing in the universe that's twice as affected by gravity is the photon. Now, the argument could be made, well, is magnetism also 2x affected by gravity? Can I bend magnetism with gravity? Because, it's the same force moving the same speed. Can gravity be bent by gravity? I mean, it just doesn't make any sense. It's nonsense. Anyway, the whole theory is just wrong, and you can point out these theoretical problems that just don't make any sense. Photons are twice as affected by gravity. Why? Doesn't make any sense. The smallest thing is the most affected, the thing that almost doesn't have any mass. But anyway, let's go on with the story. So anyway, the Eddington experiment is basically this idea that there's enough deflection here that we can see the star in the wrong position because of the gravity. Okay, because the light gets bent enough around the sun. Now the trick is Eddington was smart enough to know he can't look inside the plasma of the sun, so you can't, you have to be outside the range of the corona of the sun. So there's this almost a whole radius of distance from the sun where there's a whole bunch of electrons and protons and all kinds of particles. Now obviously if you shoot light through a bunch of particles, you could scatter. Some will scatter this way, some will scatter that way, this way, and one of these ways will actually be where we are. So scatter can actually create the shorter path. Okay, scatter can make some portion of the light get to us. So they have radio experiments where they can see objects come out from behind objects, so they can see them before they come out. Well, they see them because the light's being scattered, and by scatter, every perspective will be able to see something sooner than it should, because the scatter will scatter in all directions and you will see it. So it's just like fog works the same way. It kind of bends light. It allows light to go places it wouldn't be able to go because the scatter allows the light to get there. So obviously scatter can create the illusion of bending light, but you're not really bending it, you're just refracting it off of pieces, and it's a completely different concept than being bent by gravity. Now, all the other experiments except Eddington rely on scatter. It's stuff inside the corona. And so as the one NASA scientist admits, NASA has never seen bending outside of the corona. So all the bending that NASA's ever seen through its radio telescopes and all this other stuff, all of the bending has always been within the corona or the atmosphere of some object, where scatter is the possible explanation. And they can't tell the difference between scatter and bending. All they know is the photon got to them. They don't know whether it bent there because of gravity or it got there because it refracted off of an atom. So all the other experiments besides Eddington are kind of useless as evidence. So anyway, so the Eddington experiment did find this proper deflection. Now the point is that the Eddington experiment was, it did find the right amount of bending. We'll make a curved line. Okay. So the fact is that it's a 100-year-old experiment done with a 12-inch telescope, 12-inch big lens, and the telescope itself was 12 feet long. Okay, so this is all has to do with how you get better resolution, a longer telescope, blah blah blah. Lots of things are important. So it's not it's not a very big focal length, but it's not a very good. No, it's a good focal length, but not a very good but not a huge lens. Anyway, and Eddington got 1/10 of the quality of the photographs he was after. He figured to get 10,000 stars. He'd see 10,000 stars in his photographic plates, 10,000 stars to choose from. He only got 1,000. All right, so a huge reduction in the quality because of bad weather. So the quality of the images sucked, and both experimenters had weather problems, and they had problems with a lot of their film being compromised, and so they had a lot of problems. Eddington said in his own journal, "I wouldn't stake my life on these results." Now let's understand that he didn't say that in the New York Times article. So when the New York Times said Einstein proven right, it didn't say, but Eddington wouldn't stake his life on it. Okay, so it didn't tell the truth. And it's never been repeated. So it's never been repeated with commensurate technology. That is, using a better telescope, but bigger than 12 inches. And it's never been done from space. From space, you don't have to you don't have to wait for an eclipse. So the only way you can see next to the sun is you have to wait for an eclipse, so it gets all black out here, so you can see all these stars. But from space, it's always black right next to the sun. So you can do the experiment anytime you want to from space. And with all of our technology, all of our satellites, all of our cameras, all of the stuff, they've never attempted the experiment, or never admitted attempting the experiment. So there's absolutely nothing done. So one of the most critical experiments in terms of proving Einstein right, making Einstein a household name, has never been repeated. And this is supposed to be something fundamental to the scientific method, is you got to repeat the experiment. You got to be able to prove that you got the right results, that it wasn't a fluke or an accident or a mistake. No evidence that they have that kind of standard for something this fundamental. And again, there are logical incongruities here. The evidence doesn't work. There's lots of places in space where we know there's really strong gravity, really strong gravity, and yet we don't see any lensing at all. We don't see any light from weird places getting bent a whole bunch and coming to us. Nothing. So there's tons of places where it says the theory can't be right because the evidence is not clean. There's counter evidence. There's evidence existing that refutes the theory, yet they don't talk about that. They won't explain how it doesn't work, that it doesn't fit what we see. They just ignore that part, so they totally quote mine the evidence. All right, interferometers. Been over this one so many times. So this is the whole LIGO thing, but it just has more to do with how accurate a measuring device this is and what people think it's actually doing versus what it's actually doing. And so I can bring up lots of stuff about, how can it be? You have to know it's not two equal beams. So we've been over this. I don't want to, redo the same videos over and over again. But the truth is that this one beam is reflecting off this surface, and then it's reflecting off this surface, which are different distances, of course, and then finally reflecting off of the mirror. So there's three different sources of the reflection, and the light that goes through gets diffracted because it's going through small openings, and that's the rule of small openings, is they spread light. So one beam is spreading through the whole experiment, the other beam is not. Clearly the two beams when they come out are going to be different beams because one spread through the whole experiment is coming out much wider, so and the other one is obviously spread less, and so there can't be equal beams, can't be understood as equal beams, so that doesn't work. The other question would be is how can you detect 1/10,000th of the distance of a proton? 1/10,000th they're claiming. When your mirror, the mirror you're reflecting the light off of, can't guarantee you how deep you go into the mirror. You might go 10 atoms into the mirror. You might go just 2 atoms before you reflect. You might go just 1 atom. It's completely probabilistic in terms of you just don't know what each beam is going to be doing. They send this through the mirror 800 times. 800 times to this mirror, 800 times to this mirror. 1,600 mirror interactions. And yet after 1,600 mirror interactions, they're saying they know how far this photon has traveled within 1/10,000th of a proton. It's impossible, quite obviously. They can't guarantee the reflection off the mirror with this kind of accuracy. How can they possibly say they're measuring something this small with a ruler that's changing by more than that distance through every permutation? And they're doing it 1,600 times. They're exposing the beam to 1,600 fluctuations in distance, and yet claiming this kind of accuracy. It makes no logical sense. How can that be credible evidence? How can you people take that as serious evidence of a fact, or that that's a reality, that claim can at all be consistent with the truth? What else? All right, why hasn't LIGO been tested? Why? I mean, yes, I understand it might have some military purposes and they can't give away too much information, but we have absolutely no evidence. You know, they have a mirror dangling from some strings and they have all this crap. Why don't they just swing a weight over the top of the LIGO mirror, you know, outside the big tunnel, and demonstrate that they can detect that mass swinging, the change in gravity is, you know, wobbling the mirror. Why can't we have one test of this thing to see how accurate it is? Not a single explained test. They'll just tell us stories about how, you know, they heard a bird flew over it and farted. You know, a bird flew over the tower and it farted and they heard it. You know, some kind of crap like that. You know, people driving their cars down the street and, oh yeah, it bothers our tunnel. You know, just a bunch of anecdotal crap. No precise description of how accurate, what tiny noises this thing can detect. Because frankly, it's trying to detect a noise in space that is so silent. Again, Einstein said you'll never hear it. Yet, why was Einstein wrong? Keep asking the question, why was Einstein wrong about that? You think Einstein's right about this stupid bent space crap? You think he's right about this relativity crap, but you don't believe him when it comes to things like Einstein rings and gravitational waves? All of a sudden, Einstein doesn't know what he's talking about? All right. Let's see. How can masses replace light to less than from, I don't know what that means. Okay, how does convert to bent space? Yeah, well, turning the matter into bent space is just a bizarre, I mean, who validated that theory? What corroborating evidence do they have for this concept that two heavy things, black holes, whatever, crash into each other and they actually create something called bent space? Where was that theory tested by anyone? Certainly isn't Einstein's theory, and yet they're putting his label on it like he said it or something. He never said that. Beams aren't equal, clearly. Okay, reflect off the glass. So I think that's enough of that one. All right, polarization. Now, I've argued a simple argument for how polarization is created. And polarization is just really, the fact is that the wavelength of a frequency, the distance, this distance, ends up being the same as this distance. So how much it takes up, how much space it takes up is the same as how much these vibrations are. And the real way to understand that is just to understand that it's all about the speed of light. So when the speed of light, when electricity or something moving the speed of light hits a material, it can only move so far through the material in the amount of time between the pulses. And so to send the signal, it can't somehow go all the way out here and send the signal, because that's going to take too long and the signal would come out at the wrong place. You know, so the length is tied to the width, the speed, and it's really just the speed of light. So if you have a microwave frequency, you know, a 10 gigahertz frequency, well, yes, the antenna is only 3 centimeters long because that's how long it takes at the speed of light to go 3 centimeters. That's how far you can get up the thing and still be sending the right signal. If you have to go further up the antenna, well, you've already lost your chance to blip, to poke it out. It can't poke it out here because this won't be in the right frequency then. It'll be much later. You see, you can't make this frequency. If you wait for the electricity to go this far up the antenna, it's already way too late and you're sending the bit is way too far apart. So the only way you can send the signal is to only use 3 centimeters. You could use 1 centimeter, but the point is the length where the antenna becomes useless or superfluous or unproductive is this length. Anything longer than that's not going to do you any good. Not any substantial good, because you won't be sending photons at the right frequency. They'll still have the right phase, but they just won't be. You won't be creating rays of photon. You'll be creating rays with huge breaks in them. You know. So anyway, so that's one thing to understand. Why isn't that a good enough explanation of what polarization is? And so polarization would be when it's just clearly, this is just the wave is just a representation of the fact that this is where the clump is, the clump is, the clump is, and the real key is the distance between them. You know, and that's the real explanation. All right. Clearly, they have this idea of the polarizing film, and I've already pointed out. You know, you put a third film in at this direction, and more light comes out. So you put an extra filter in, and you get more stuff out. Obviously, this first filter does not absorb photons. It doesn't get hot. Doesn't melt. The photons are still here when they go through the first filter, and all you're doing is putting them back in phase again by putting them through another piece of plastic and changing their phase, and so now you can recover some of them, and that's all that's really happening in the experiment. It's just changing the phase. The photons are still here when they're invisible. Okay, they're still coming out of the filters, and you don't see them because there's slight defects. The defect would be that the photon isn't long enough. Like, it has to have 6 bits, 6 waves to be seen. If it doesn't have the 6 waves, we can't see it. Now, Frog could see it, but we can't see it. And so some of the photons are broken in the sense that their ray length is too short. And then some of the photons are broken in the sense that they have 2 things at the right frequency, then they have a gap, and then they have 2 things at the right frequency. So again, they're kind of too small a piece, and the pieces have been intersected by one missing piece. So you're just really destroying tiny bits of the photon. The photon in substances makes through all the filters. It's just that they've been broken in subtle little ways, and those subtle little ways can be reconstructed. You can take 2 of these pieces and re-put them back in line with each other with another filter. All right, so that explains it. All right, so I don't know if I want to get the relativity stuff. Let's see what this is. Just an what the hell am I saying here? That gravity bent space moves the same speed as virtual photons. All right, yeah. So you don't think it's just a coincidence, right? It's, you know, we have bent space, which is an undefined force. Just doesn't say anything about what it is. So you have this idea that bent space moves exactly the same speed as virtual photons, that are the carriers for magnetism and electricity. And that's just a coincidence, though. 2 fundamentally different kind of concepts. One of them that's quite quantized, quite discrete bits of momentum, and one that doesn't have any definition. And it's just a coincidence that they're moving at the same speed. I mean, do you really think that's what it is? There really are fundamentally different forces, and it's just a coincidence? I mean, obviously, this QM thing, the virtual photon idea, and the bent space idea are not compatible, and one of them, if not both of them, have to go. I would argue there's good reason for both of them. There's certainly good reason for bent space to go. It's just nonsensical. This bent space-time, this whole idea that time is a dimension is nonsense. Time is obviously just a function. It's a function of movement. It's the speed at which things can capture distance. The fastest thing that can capture distance is this idea of a force bit or a photon. That moves the fastest. That's it. That's the standard. That's time. Everything is based on that speed. And everything indicates that that's the real frame the universe functions in, that the photon is always what you can go to. You're a little confused about what's going on. Watch what a photon does, and you'll know what's going on. You'll know how fast you're going. You'll know which way you're going. You'll know all that stuff. You just watch what photons are doing. So, yeah, it's not really in the form of a question. So anyway, so you think it's just a coincidence that all the forces move the same speed. It's just a coincidence. All these different fields, all this different function, and it's all moving the same speed by some coincidence. No, I think the coincidence is it's all the same stuff, and you're just misunderstanding. It's all the same stuff. And getting magnetism and charge, you're confusing. You don't think there's a magnetic monopole. Well, how exactly is when an electron and a proton are in this arrangement, how is that not a magnetic object? It's clearly a magnetic object. If I put another electron and proton, put a proton here and an electron here, you know what's going to happen. Okay, I mean, the thing's going to turn, and well, I should put it the same way, right? You know what's going to happen, right? I mean, the proton's going to repel the proton, the electron's going to repel the electron, but the inverse is going to be attractive. So you know the object's just going to turn just like a magnet. It's going to behave just like a magnet. It's obviously the same functionality. It's silly to make any distinction that there's something called a magnetic field and an electric field. The simple explanation for why a magnet fails to work, the north-south part of a magnet breaks down when you expose it to a charge, is the simple argument that the magnet's made out of metal and it ends up charging the surface of the magnet, clogging the filter. It just breaks the filtering capacity of the magnet. Magnet's taking energy and filtering, north energy this way, south energy that way, and it can't do that anymore when it's clogged by a bunch of insufficient number of electrons or too many electrons, and the magnet can't work anymore. Simple explanation. Alright, now why are photons twice as affected by gravity? Good question. Alright, so that's the same as that question, so that might be enough for this one. On the surface of the sun, what is used pushing pressure? Okay, so an interesting thing I'll just throw in, just because I was thinking about it, in terms of the thermal equilibrium problem. Yeah, so I'll bring that up because it's sort of interesting. Alright, so the gravity argument, a catch to a particle theory of gravity, is that objects reach thermal equilibrium. That is, you could say that an object, gets, when it's getting hot, when it's getting heated, it consumes more energy than it emits, right? So as the temperature is increasing inside of something, it consumes more from the environment than it produces to the environment. But once it reaches a constant temperature, then it reaches equilibrium. That is, the same amount of stuff comes in as the same amount comes out. Okay, it's not absorbing energy anymore when it stops. It's like stopping accelerating. When you stop accelerating something, it's not consuming any engine energy. It's just coasting, and the same thing is with heat. It'll just sort of coast at thermal equilibrium. So you can make the same argument that gravity has the same kind of problem, in that you could understand why it would absorb energy to create the gravity, right? But once the gravity is created, then it's going to be thermal equilibrium, and it can't possibly be absorbing energy. But the trick to this whole thing is that energy is a very interesting thing. So if I was to make an experiment where I hit something with a bunch of little tiny bits of energy, I could have a total of 10 pounds per square inch or something of energy, and that the energy would move the object. It's getting hit by all these little bits, it absorbs the energy and it moves. But if I took all the energy and I took that 10 pounds per square inch and I made the 10 pounds per square inch 1 millimeter thick, obviously now it's 1,000 pounds per millimeter. If I turned it into a bullet and I shot a bullet at the target, well, the bullet could go right through, and most of the energy could end up going, just a tiny bit of the energy would be absorbed, and most of the energy would continue with the bullet. So I can convert energy. So the key to gravity is gravity is always absorbed. All the gravity that goes in, so to speak, the little tiny bits are absorbing the gravity. So all the gravity energy is absorbed by the little bits. But the energy that leaves the Earth is in the form of heat, clumps of stuff. Okay, big stuff is leaving, bullets. And the big stuff breaks things, tears them to pieces. It goes through them. So it's like, let's say you tried to, I thought of this because I was thinking about, the fact that the sun has all this heat energy coming off of it. And what happens if I tried to go towards the sun with like a big flat plate? All right. And so one side of the plate is hitting all this fire on one side, all this pressure, and there's no fire coming from this direction. So clearly there'd be this pressure from all this energy coming off the sun, all these zillions of photons, all this heat, all this stuff is going to push the plate away. But what it's really going to do is melt the plate. Okay, it's going to disintegrate it. It's going to shoot a bunch of bullets through it. Boom, 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 boom. Break it into little tiny pieces, and and so you're going to lose most of the energy. So most of the energy coming out of the sun, you're not going to be able to catch it because you can't make a parachute to catch that heat. The heat destroys any parachute you make. So any kind of sail you make to try to catch the wind of the heat coming off the sun, the sail will melt. We don't have any mechanics for that. It'll just disintegrate it. It'll break it into little tiny pieces, and most of the energy will be in the form of scattering little bits. But the idea would be is that how much is the energy, the heat pressure of the sun, what is that pressure in pounds per square inch, if I could measure it, if it didn't disintegrate my scale, if the scale could survive, how much is the pressure per square inch, or the meters per second in force, versus the gravitational meters? It's 80 meters per second gravitationally on the surface of the sun. What's the pressure out from heat? And that would be a very interesting question to see what the balance is between those two things. But the real point I wanted to make is that the energy that the Earth, say, for example, absorbs through gravity is energy it's emitting as heat from its hot core, and particles and little bits and all the rest of the shit that's coming out of the Earth. The radiation that comes out of the Earth is in the form of different kind of mechanism, a kind of heat. Okay, like gravity is the finest heat you can get, but heat, like cosmic rays and X-rays and light and different things, those things will break pieces. All of the energy won't be absorbed because the energy will be absorbed in breaking the material into pieces. And so it won't be as effective in terms of being absorbed, and therefore the force of gravity will be stronger than the force of the emitted force. So what goes into the Earth is gravity. It all gets absorbed, and it's radiated back to the world in a form that's harder to absorb. The form of the heat radiation coming off the Earth is not very effective because it goes around, it pushes through, it bores holes in, but it doesn't get absorbed by all of the nuclear bits. It can't get through the surface of the object. All right. So it also gets to the subject of what a pure reflection is. Reflections usually have to do with an absorption of energy and then a release of energy, so that the thing you hit doesn't absorb any of the energy. So obviously reflections, if you're reflecting the heat, you're not going to be moved by it. Whereas if you absorb the heat, you're going to be moved by it. So it's a critical difference. So the energy, the gravitational energy, you completely absorb. The energy that's coming off the Earth, you don't absorb. It reflects off you, and therefore one force is much stronger than the other force, kind of a thing. But anyway, that's a whole nother sort of a separate subject. But anyway, so there are questions sort of in this video, enough of them to be answered. Why are you so confident in a theory that it's so poorly evidenced? And that's really argument I've made from the beginning, is that the evidence is so weak. How can you be closed-minded to simpler, better explanations of what's happening in the experiments? Simpler, more complete. And my argument is there are simpler, more complete answers to the questions of how does whether there's things orbiting atoms. I didn't get to that subject, but their whole orbiting model can be wrong. There isn't enough evidence to say you're sure it works that way, and that's the whole point. All of this evidence is really weak, and you can make a better model, one that doesn't have bent space, virtual photons, dark matter, dark energy, a bunch of invisible magical forces. Even things like saying something like the magnetic field. Field of what? Field functioning how? Field doing what? It's just a vacuous explanation for what the mechanism is. And you can have a better explanation of a real mechanism you can draw a picture of. So why are you so belligerent that they've got the right answer? Why are you so certain they have the right answer when there are so many elements that don't make any sense, that do create contradictions in their own theory? You can't say 1 minute, that a single slit makes two waves, and then the next minute say, no, not when I put them next to each other, they don't. You can't do that kind of, you can't use, it's just duplicity. You can't claim a theory is right and then not use it in another circumstance because it's inconvenient. Alright, enough of a video probably. So hopefully I won't have any further, hopefully it saved this one properly. So till the next time and such.